Okay, so this is our first example from chapter 14. So this is chapter 14, and out of your packet, it is page 6, and I'm doing example number 1. So let's read carefully. This says, a college's data about incoming freshmen is normally distributed. So I'm just going to go up here and write that this is the college's data about incoming freshmen. That's all the incoming freshmen, so that's going to represent our population. It says the mean of their high school GPAs is 3.4, and they have a standard deviation of 0.35. The students are then randomly assigned to freshman writing seminars in groups of 25. So that right there is an N, a sample size being provided. And our first step here is to describe the sampling distribution for all samples of size 25. So we know the distribution, this is the population distribution up here that came from our paragraph, and we know that's normal. Now, because the population distribution is normal, by the central limit theorem, our sampling distribution will also be normal. So we are now looking for a sampling distribution that looks something like this. Now remember, we're talking means now. This isn't the sampling distribution for proportions. What we do is we replace the same mean that we were using for the population. That doesn't change. Then what we do is we reduce our standard deviation based on the sample size. So we take the original standard deviation and divide by the square root of the sample size. So I'm going to go ahead and break that down one more step here. This would become 3.4 and then 0.35 over 5. That's the square root of 25. So my new model has a mean of 3.4 and a new standard deviation of 0.07. Really, really small compared to the old standard deviation. Okay, so now the question is, are parts B and C referring to the population or to the sampling distribution? Now, if it's referring to the sampling distribution, then it's going to be referring to a group of people of size 25. If it's referring to the population, then it's just going to be referring to any random student from the group. So let's read carefully. Find the probability that a student has a GPA greater than 3.1. So this is any student GPA greater than 3.1. Now, this any student is referring to somebody straight out of the population, not a specific group of students, like one of the classes altogether. So this is going to be using normal CDF because it says find the probability. Remember that language is normal CDF. That's the language we're going to use. And here we're going to be using 3.1 as our provided lower bound. So this is going to be normal CDF. 3.1, 1E99. We make up our upper bound when it's not provided. And then we put in the mean and standard deviation from the population. So we're using the 35 here, the 0.35. And the answer here is 0.804. Okay, let's read carefully here for the next part. Find the probability that one of the groups has an average GPA. Okay, so first of all, this same language, find the probability, still means we're using normal CDF. But now we're talking about a group average. So this is the group average GPA is greater than 3.1. So this is now referring to my sampling distribution, because we are now talking about an entire group at this having a GPA that's greater than 3.1 on average. So taking all 25 people, averaging them, and that being larger than 3.1. So that means we're going to use our new model that we found in Part A, and this is actually the same exact setup, except we're going to switch out our standard deviation for the smaller one. So here, we still have 3.1 as our lower bound, 1E99 as our upper bound, 3.4 is the mean, but now because we're referring to the groups, 25 at a time, our standard deviation is 0.07. And when you put this in the calculator, it's like a series of nines, like 5 of them. So 1, 2, 3, 4, 5. Or if we were to round to something more reasonable, we would actually say that there's a 100% chance the group has a GPA greater than 3.1, because we've now collectively got 25 people together to average out. Okay, I'm going to do another example for sampling distributions for means, so catch that in my next video.